sets. We actually we were introduced to the idea of sets. I actually snuck them into at the very end of fractals. What was the second last? What was the second last fractal that I showed you? It was the most complicated one of all. It was the Mandelbrot set. I wonder if you caught me saying that, right? So sets, right? A set is the first kind of term, right? That's the first idea. And the way we denote a set is with curly braces, like this. Okay? You're probably not very good at drawing curly braces because we don't do them very often. They should look like this. It's easier if you do them bigger. You'll get practice, don't worry. Just like when you see something like this. Okay? You know that those are coordinates, right? We're used to that kind of thing. And so when you see curly braces, think a set, okay? So you would put things inside here, okay? So a definition of a set, all it is, well, how would you define a set? Because you've used this language informally before. A set of things.
It says irrelevant, but apparently set has the most meanings, like, more than any other word.
As a word?
Yeah.
That's interesting. That's interesting because, well, why would it have so many meanings? Yeah, even volleyball. Anyway, a set it's a collection of elements. A collection, or a group if you like, of elements. I'm actually going to avoid the word group because in maths, group means something else as well. Okay. You could say a collection of items, but in set theory, we actually call them, they're supposed to be called elements, right? Objects or items or things that can fit in here. We can put them all together. Okay, so an example. I'll give you a couple. Okay, for instance, I could give you this. That's an example of a set, right? This set is a finite set, right? I'm going to throw out occasionally some words which you don't need to devote a whole row to, but they're important words. So, for example, that's finite. Okay, but you don't have to just have a finite set. You could have an infinite set, right? It could go on forever. For instance, this is the set of all odd numbers, and it goes on forever, okay? Sets can also include sets within them as elements, but we'll get onto that a bit later. Okay, diagrams. Now over here, we're very familiar with the main kind of diagram used to illustrate sets, like this. And they're named after a guy. The name starting with V. Does anyone know what it is? Venn diagrams. That's right. Venn diagrams. Now, some of the things. Come in. Hello, come on. Come on. You have to go to this ammo in HSI.
Come back in 1 piece.
Okay. Sorry, where were we? Venn diagrams, right? Venn diagrams. Now, we're very familiar with these kinds of things, right? That second one's not bad. This is the typical Venn diagram. But as you will see, as we'll move through these, right? Venn diagrams are anything which represent a bunch of sets that relate to each other. That's all, okay? So for something like this, well, okay, I guess we can just write it like this. 2, 4, 6. These two sets, here's actually an important word. We've introduced this idea of a finite set and an infinite set. Another word for you, which is not worth putting on its own row, is that these two sets, the ones I've named, they are what we call disjoint sets, right? Disjoint sets, which you might be able to tell based on this example. What does that mean? Disjoint sets. It means they have nothing in common with each other. No overlap whatsoever. So if I were to draw a Venn diagram to illustrate these two sets and how they relate to each other, well, it'd be pretty boring. It wouldn't look like this because these are not disjoint, are they? You just have two separate bubbles. That's it. Okay, so there you go. Simple. Right, let's rule that off. Okay. Now, where it starts to get interesting is, as I said, when you've got more than one set together and they relate in some way. Okay, so here's our first important way to connect sets together, which is intersection. Okay. There's a keyword for this, which is and. And the symbol that we use for it, sets tend to be denoted by our capital letters, okay? So if I wrote this, A, and then I draw this arch kind of shape, okay? So it's not quite it's not a semicircle, okay? It's kind of taller than that. It's kind of like a upside down U without the taily bit, okay? We'll get to that in a second, okay? So intersection means, well, what do you think the word indicates? It means that, yeah, there's a, here we go. There's a bunch of elements that are in both sets, okay? So intersection, I would say it's the elements in both, in this case, set A and set B. Objects or elements that belong in both sets. Okay? So let's give an example. Okay, let's say if I gave you this, I'll go back to this example. 2, 4, 6. We'll call that one A. Okay, and let's set out another one. Let's call B. Let's call B all the prime numbers under 10. What are all the prime numbers under 10? You got 2, 3. 5 and 7. Okay, cool. So you can see here, this is a little more interesting. There is an overlap between these. If I said A intersection B, right? Or A and B at the same time, okay? Which objects are in there? It's just 2. 2 is the only number that's in both of them, okay? So I would say like this. Okay? The intersection of two sets is also a set, so that's why I've got curly braces around it. Let's draw a quick diagram. Intersection would be this area in here. There you go. Okay. Now, the big brother to intersection is union. Okay, union. Okay. Now, just like intersection has a keyword, and union also has a keyword. I'll let you think about what it is in a second. Okay. Now, the symbol for union is the upside down symbol of intersection. So it actually does look like a U, just without the tail on it. Okay? In fact, that's one of the ways you can remember which one's which. This one looks like, literally, union, right? And that one looks kind of like intersection. I don't know, it's a bit of a stretch, but it works. Okay? So the keyword for this was and. Union means give me everything in both sets. Okay, so the keyword for that would be or, right? A or B, right? If it's one or the other, no big deal. Okay. Right, so this would be not just elements in both set A and B, right? This would be elements in set A or set B. That's all. See, I'm using the keyword there. You see it? Set A or set B. Okay, so again, if I just use the same A and B that I did here, right, then A union B will be equal to, well, it's going to be 2 all the way up to 7. There you go. 3, 4, 5, 6, 7. By the way, just to note, I wrote this, right, but I could equally have written this. 7, 6, 5, 4, 3, 2. Okay, or I could have written 2, 4, 6, 3, 5, 7. Okay, the idea is that order doesn't matter. Order doesn't matter. These two, and this is an important idea, these two are equal sets. They are the same set, right? If order is important to you, then you do not have a set. You have, what word do we use when things have an order to them? Also starts with S. Sequence, right? We want things to be sequential. Things like, say, the Fibonacci sequence, right? It's not the Fibonacci set. Who cares about that? That's not very meaningful, but when you've got them in an order, then it's interesting. Sets, we don't care where they are. Okay, so these two are equal sets. Let's draw a diagram. If you got two overlapping like this, what would the union be? Yeah, you color in both circles fully. Like so. Okay, now I'm about to run out of space, but hopefully you've got a bit more to go. We have lots more ideas, but the next one is called A. And then there's a couple of different symbols for this, okay? So that first one is a triangle. It's actually a capital delta. Or you might also see this. It's a circle that's halved. Okay. The two, just like it's got two symbols, it also has two names. And they're both pretty cool, I think, okay? First you got the full name, like this, right? So this is called the symmetric difference. Right? That's a pretty fancy name, okay? There's and, there's or. The key phrase for this, the key word, is XOR. Okay? It's not red XOR, it's XOR. Okay? The X is an initial. It stands for exclusive. Okay? Now, here's what I'm going to do. We've so far been going across the table. I'm going to draw this for you, and I want you to tell me how you define this, okay? It's not the intersection, it's not the union. The symmetric difference or the exclusive or looks like this. This would be A triangle or A XOR B. How would you word this? Yeah.
Those values in set A or in set B, but not in both.
Good. Yeah. So you can see that it's one or the other, but it's exclusive, right? It's exclusively A or it's exclusively B. It's not both at the same time. Okay. Yep.
Yeah. Is the second symbol the same as both of those?
These both mean the same thing. It's just that you'll see this. See, set theory is a really interesting and wide-ranging topic. So lots of people use it, and whenever you got lots of people using the same kinds of ideas, they always make up their own notation. Okay. The same thing will happen when you guys get into calculus. Most of you next year, because so many people use calculus. Everyone's got a different way of writing it, which is frustrating. But once you get the hang of it, it's not that big deal. So we would say elements in. You can say this two ways. One way you could say it is in either set A or set B, but not both. Okay? Or you could say elements in exclusively set A or exclusively set B. They're both saying the same thing. Okay? So what would A XOR B equal to? I'm going with this as A and B. Right?
Everything except 2.
Yeah, that's right. Because 2 is this number in the middle, right? Just like I said here. Now can you see I'm already starting to get some relationships between the things in this table, right? It's going to be, let's see, 3, 4, 5, 6, 7. Okay. Really, it's this, the union, minus the intersection. I mean, you can even see that visually, right? This is this minus this. Right? So you can say it's A union B minus A intersection B. Make sense?